Hello, I'm Ashish Arora. I'm working as a senior scientist at the Molecular and Structural Biology Division, CSIR Central Drug Research Institute, Lucknow. I work in the area of structural biology and my specialization is in determination of protein structures using NMR spectroscopy. Here I will present module number 22, NMR signal detection and data processing of paper 8, medical physics for the EPG Pathshala. The objectives are to present to you what are the components for detection of NMR signal. In the previous module, we have seen how we irradiate the sample, and now we will see how we detect the NMR signal. What is quadrature detection? We will try to understand it mathematically as well as in terms of the setup. What factors are important for sampling the NMR data? How is the raw NMR data manipulated to give sharp frequency domain signals? What is the effect of pulse width and receiver gain on signal strength? What is the effect of acquisition time and scan repetition rate on NMR signal? What is phase cycling and scan averaging? Let's start with radio frequency receiver. The receiving coil is same as the transmitting coil. However, the routing of the signal is different. After being picked up by the receiver coil as an oscillating current in the range of milliamps, the signal is routed to the preamplifier. The preamplifier provides an initial stage of amplification of the NMR signal prior to further detection and processing. To minimize transmission losses, the preamplifier is placed as close as possible to the detection coil. The quality of the preamplifier determines the maximum signal to noise ratio that can be achieved. The frequency of the signal is reduced to an intermediate frequency range and the signal is split into two channels by mixing the signal with a reference frequency which has a phase difference of 90 degree for the two channels. Signal to noise ratio of the receiver. The main factors contributing to the basic signal to noise ratio of NMR measurements are the sample concentration. Higher the concentration, better the signal to noise. Gyromagnetic ratios gamma E and gamma D of the excited and detected nuclei respectively. This is for the multi-dimensional experiment. For a single pulse experiment, the excited and detected nuclei are the same, usually the proton. Static magnetic field strength B0. Higher the field strength, the better signal to noise ratio would be. Then there are factors related to the probe, coil design factor K, receiver bandwidth delta F in Hertz, the resistance and temperature RC and TC respectively of the coil, noise temperature of the preamplifier TA, sample temperature TS and resistance induced by the sample in the coil RS. So, this actually prevents very high ionic strength samples to be used in NMR. The usual strength that was used was around 50 to 100 millimolar sodium chloride, which has now been increased to 250 millimolar sodium chloride in the sample. In conventional NMR probes, the signal to noise ratio is limited ultimately by thermal noise in the RF coil and preamplifier. Cryogenic probes increase signal to noise by cooling the RF coil and preamplifier to reduce the noise contributions from these sources, and these probes are becoming very common, especially for the analysis of biomolecules. Quadrature detection. Quadrature detection allows the determination of both the sign, which may be positive or negative, and absolute magnitude of the offset frequency. To determine the sign of the frequency, both the cosine and sine components of a harmonic signal need to be recorded. After the NMR signal has been transformed to intermediate frequency, the signal is split into two channels. The first channel is mixed with a cosine modulated reference frequency, while the second channel is mixed with the same frequency but with a sine modulated phase. The mixing reduces the signal frequency of the two channels into the range of a few tens of kilohertz. The signals are separately digitized for each channel with the help of high dynamic range analog to digital converters, which sample the signals at discrete time points. The magnitude of the detected signal must not exceed the dynamic range of the ADC. This is called as ADC overflow. Normally, ADCs oversample the data and digitize a frequency range that is much larger than the one desired. The digitized signal is submitted to digital filters, which rejects all noise and possible signals outside the selected spectral range of typically a few kilohertz. After digitizing and filtering, the signal is sent to the computer memory, where different scans are summed up for later processing of the data. This quadrature detection scheme allows reduction of the bandwidth to be measured by a factor of 2 and concomitantly reducing the noise by square root 2. So, here is the schematic representation of quadrature detection. First, let us see the hardware. There is a signal ST which is sent to the splitter. This signal is coming from the preamplifier, and here the signal is mixed with reference frequencies. 0 degree means cosine modulated and 90 degree means sine modulated. Then the range is filtered and then the resulting signal is digitized, and this is the real signal. This is called as the real signal with cosine modulation, whereas the 90 degree reference, when it is added, the signal is called as the imaginary signal. The incoming signal recorded by the probe and preamplifier is split into two parallel channels. The signal in each channel is mixed with a reference signal, passed through a low pass audio filter and digitized. Orthogonal components of the signal are obtained by shifting the relative phase of the reference signals by 90 degrees. Now, let us look at the peaks. So, if the signal was modulated only by one reference frequency, say cosine frequency, a single coil generates a signal modulated as cos omega 0 t that yields signals at plus minus omega 0. So, that there will be two peaks. The signal is mixed with reference signals modulated as cos omega RF t and as sin omega RF t to generate signals as plus minus omega 0 minus omega RF and plus minus omega 0 plus omega RF. Because the sine function signals at plus minus omega 0 minus omega RF and plus minus omega 0 plus omega RF, because the sine function is odd, the symmetric signals are inverted, as you see in the second set of peaks. The filters remove the high frequency components so that only low frequency components remain in the spectra J and K. Then these two are summed up so that the frequency domain spectrum obtained by summing J and K contains only a single resonance signal at a frequency omega is equal to omega 0 minus omega RF. Now, once we have the signals, then we have to process the data, and the mathematics of Fourier transformation is described here. The time domain signal for a damped oscillator is given by St is equal to I0 exponential bracket I omega 0 minus lambda 0 bracket closed bracket t plus t0 bracket closed plus I phi 0. I0 is the initial signal amplitude, omega 0 is the frequency, lambda 0 is the decay constant, usually the transverse reflection rate constant. Phi 0 is the initial signal phase and t0 is the value of the initial sampling delay. The Fourier transform of St is S omega, and there is this expression determining it, I0 exponential and then the second I0 exponential, in which the absorption A omega and dispersion d omega, as we have seen before, these line shapes can be expressed as A omega is equal to lambda 0 divided by lambda 0 square plus bracket omega 0 minus omega bracket close whole square, and the dispersion dW is equal to bracket omega 0 minus omega bracket close divided by lambda 0 square plus bracket omega 0 minus omega bracket close whole square. The absorptive and dispersive Lorentzian line shapes. The Fourier transform of an exponentially damped sinusoid generates a frequency domain signal with real and imaginary components described by the absorptive and dispersive Lorentzian functions as shown in A and B respectively. The line width of the absorptive Lorentzian is defined as the full width at half height FWHH and is given by delta omega FWHH is equal to 2 lambda 0, where lambda 0 is the transverse relaxation rate constant or R2. Data acquisition. The NMR signal is a damped sinusoidal voltage versus time signal and it is discretely sampled. The delay between each sampling point is referred to as the dwell time. The dwell time is defined by the spectral width SW is equal to 1 by tau dW. The Nyquist frequency Fn is equal to 1 divided by 2 tau dW. This defines the highest frequency that can be uniquely sampled when the dwell time is set to tau dW. The sweep width ranges from minus Fn to plus Fn. The experimental frequency domain spectrum is calculated from the time domain spectrum or time domain data by discrete Fourier transform by using the fast Fourier transformation FFT algorithm. The use of the FFT algorithm requires that the number of data points n must be an integral power of 2. A number of digital signal processes are applied to and after Fourier transformation in order to maximize the information available from the spectrum. Data manipulations, zero filling. Zero filling or zero padding is the process of appending a sequence of zeros to a data sequence prior to Fourier transformation, which results in improvement in digital resolution. The fast Fourier transform algorithms require that the number of data points n should be equal to an integral power of 2. If 2m minus 1 is less than n is less than 2 to the power of m for an integer m, then prior to Fourier transformation, zero filling is used to generate a new data sequence of 2m points in which all points greater than n have the 0 value. If 2 to the power m minus 1 is less than n is less than 2 to the power m, then real improvement in the information content of an NMR spectrum is obtained by zero filling to obtain a sequence of 2 to the power m plus 1 data points, that is twice the number of data points. Additional zero filling results only in cosmetic interpolation between data points in the frequency domain. The time domain data can also be extended by linear prediction using the singular value decomposition algorithm. Apodization. NMR data is collected during the acquisition period, after which it is abruptly cut off before it reaches to 0. Zero padding at the end of such abruptly truncated data results in sinc function truncation artifacts. Apodization or windowing is the process of improving the properties of the spectrum like line shape, signal resolution, truncation artifacts or signal to noise ratio by convoluting the spectrum with a more satisfactory line shape or window function to enhance particular regions of the FID and to smoothly bring the data to 0. Many apodization or window functions are available in data processing packages. These can be divided into three types: exponential multiplication, Lorentzian to Gaussian transformation, and the trigonometric window functions. The exponential multiplication leads to reduction in noise but with line broadening, that means loss of resolution. The Lorentz to Gaussian transform suppresses truncation artifacts and converts the Lorentzian line shape to a Gaussian line shape. Gaussian line shapes approach the baseline faster than Lorentzian line shapes, providing some enhancement in signal resolution. Trigonometric window functions remove truncation artifacts by bringing the FID to 0 at the end of the acquisition time and by enhancing resolution by increasing the contribution of later time points to the transform. The early portions of FID are low resolution, the later portions are high resolution, while the noise level remains the same throughout. The cosine window function is most frequently applied to truncated NMR signals. There is a schematic representation to demonstrate apodization. On the left, you see a signal which has been truncated and then zero padded. When you Fourier transform such a signal, then the spectrum is shown below. The peak has wiggles which are called as the sinc function artifacts. Then when you apply an exponential window function, then the FID is more smoothly brought to 0, but as you can see that the line width increases. And when a cos function is applied, then you get most optimum results as shown in the right side, the FID multiplied or convoluted with a cosine window and the result of Fourier transforming which is shown below that. Phasing of the signal. The frequency domain signal generally displays a frequency dependent phase error. The spectrum is seen to be a mixture of absorptive and dispersive line shapes. To obtain a pure absorptive line shape, phasing has to be done by applying frequency dependent phase correction function theta omega. Theta omega is equal to theta 0 plus theta 1 bracket omega minus omega pivot bracket close divided by 2 pi SW is for spectral width, in which theta 0 is called the 0 order phase correction and theta 1 is called the first order phase correction and omega pivot is called the pivot frequency. The 0 order phase correction is frequency independent, while the first order phase correction contributes to a linearly frequency dependent phase. The frequency dependent phase correction is 0 at omega pivot and has values of minus theta 1 bracket 1 by 2 plus omega pivot divided by 2 pi SW bracket closed and theta 1 1 by 2 minus omega pivot divided by 2 pi SW bracket closed at the two edges of the spectrum. On modern NMR spectrometers, phasing is performed interactively by adjusting phi 0, theta 0 and theta 1 until the line shapes in the real part of the spectrum are absorptive. Here is the schematic representation of phasing. The spectra shown in A, the upfield resonance has been phased using a 0 order phase correction. However, the downfield resonance has a phase error. Upfield means towards the right and downfield means towards the left, and this is used in terms of chemical shift, which we will discuss in the next module. In B, you have the downfield resonance has been phased using a 0 order phase correction. However, the upfield resonance has a phase error. So, basically this is to show that all the peaks in the spectrum cannot be phase corrected to give pure absorptive peaks by using just the theta 0. Now, in C, you see a spectrum, both signals have been phased simultaneously by applying 0 and first order phase corrections. You have referencing. Once the spectrum has been phased, it is necessary to reference the spectrum, about which we will read more in detail in the next module. The most commonly used referencing compounds are TMS and DSS. These compounds have methyl groups attached to a silicon atom, and their proton spins resonate at a lower frequency than most other resonances in the spectrum. So, you can see the structure of TMS, it is tetramethyl silane, and then DSS is a derivative having 3 methyl groups attached to silane, and it is a sulfonate derivative which makes it soluble in water. TMS is insoluble in aqueous solution. Consequently, TMS is generally used to reference spectra taken in organic solvents, while DSS is the compound of choice as an aqueous reference compound because of its negligible sensitivity to pH and temperature changes. C13 and N15 spectra are often referenced indirectly based on the measured proton shift of DSS. Baseline correction. Due to some data acquisition factors, the phase correction does not ensure a flat baseline. In order to obtain a flat baseline, and there can be several forms of baseline distortions like baseline offset, curvature, nodes and antinodes. And for this, baseline correction has to be performed. Baseline correction defines various routines that are applied to obtain a flat baseline. In the spectra A, you see a spectrum which has a flat baseline. In the spectrum shown in B, you see that the whole spectrum is below the scale, and this is called as the offset or DC offset baseline. And then you see a curved baseline which comes because of various errors, and these kind of spectra need baseline corrections by following various routines. Let us come now to the practical aspects of doing NMR. So, for doing NMR, first of all we have to have an NMR sample, and this sample is put in an NMR sample tube. The NMR sample tube are very typical. They are thin walled, long borosilicate glass tubes. The NMR tubes have 5 mm outer diameter and are almost 8 inches in length. The sample volume required for recording the data is roughly around 0.6 ml. And the concentration, as I mentioned earlier, is from 0.2 to 2 millimolar. The NMR tube filled with sample is carefully inserted within the NMR holder as is shown in the figure on the right, and it is then centered properly with the NMR depth gauge. So, this depth gauge has a line which marks the center, and the NMR sample has to be centered along this line. It is then inserted at the top of NMR spectrometers. The sample tube goes down with gradient air pressure. So, first we have to lift the sample, the air should be coming out of the spectrometer, then we put NMR tube into the spinner, and that we put inside the magnet from top of the magnet with air pressure, and then this pressure is gradually lowered so that the sample goes inside and sits in the NMR probe. For protein samples, Shigemi NMR tubes are used. The glass in these tubes is matched to the magnetic susceptibility of D2O, and a glass plug is inserted from the top to avoid the sample air interface, and in our lab we usually use the Shigemi NMR tubes. Now, the pulse has to be applied to the sample, and we have to calibrate a 90-degree pulse length. A correct 90-degree pulse applied to the sample gives the highest signal intensity and minimizes the artifacts. It should be calibrated with each new sample. To calibrate the proton pulse length, the transmitter power is set to 5 to 10 dB decibels, less than the maximum power. Then a pulse width of 1 microsecond is applied to the sample. The FID is digitized and processed, and the spectrum is phased For positive pure absorptive peaks, a region of spectrum with sharp and strong peak is selected. Now in a set of experiments, the pulse width is arrayed with a difference of about 2 microseconds. First, the signal intensity increases till the pulse width becomes equivalent to a 90-degree pulse. Then the intensity decreases and becomes 0 at pulse width corresponding to 180-degree pulse. The signal then becomes negative and the peak becomes maximum negative at pulse width equal to 270-degree pulse. Then it again starts decreasing, and upon further increase of pulse duration, the negative peak intensity reduces and goes through 0 before becoming positive again. The pulse width corresponding to the 0 crossover point is equal to the 360-degree pulse. The 90-degree pulse width is obtained by dividing the 360-degree pulse width by 4. Then what one can do is that one can again array around the 360-degree pulse with increments of only 0.4 microseconds, so that finally one ends up with a pulse width accuracy of around 0.1 to 0.05 microseconds. Folding and aliasing. The Nyquist frequency Fn is equal to 1 by 2 tau dw, where dw is the dwell time, defines the highest frequency that can be uniquely sampled when the dwell time is set to tau dw. The sweep width ranges from minus Fn to plus Fn. A signal with a frequency that is higher than Fn either folds or is aliased into the spectrum. Folding and aliasing are defined as: folding is a peak with a frequency Fn plus delta will appear at a frequency of Fn minus delta. This effect is called folding because the peak outside of the sweep width has been folded or reflected about the edge of the spectrum. While aliasing, a peak with a frequency of Fn plus delta will appear at a frequency of minus Fn plus delta. Schematic representation of folding and aliasing is shown in the figure. On the left side, you see a spectrum which has two peaks. One of them has an arrow. At the bottom of them, there is this range marked as spectral width, SW. As you can see that one peak comes within the spectral width range, while the peak marked with an arrow is outside that range. So the folding of the peaks brings it inside the spectral width. You can see that there is a decrease in the intensity of the peak and it is close to the edge of the spectrum, whereas aliasing of the peak pushes it to the other edge of the spectral width, while the peak that is within the spectral width is unchanged. The left section of the diagram shows an NMR spectrum with two peaks, both of equal intensity. One peak lies outside the sweep width and will either be folded as shown in upper right or aliased as shown in lower right, depending on the type of data collection. Setting the receiver gain. The analog signal from the dual mixers is converted to a digital signal before it is stored in the computer. The sign of this signal depends on the amplification or gain that was applied to the signal in the receiver. It is important to accurately represent the analog signal in digital form so that an undistorted spectrum is obtained after Fourier transformation. If the gain is too high, there will not be enough bits in the digitizer to represent the signal, and the signal will be clipped at the largest value of the digitizer. Alternatively, if the gain is too small, the signal will only utilize the lower order bits of the digitizer. The result is an inaccurate conversion of the signal to its digital form because of round-off errors which introduce additional noise in the spectrum. Spectral resolution and acquisition time of the FIT. The total data acquisition time TAC defines the highest possible resolution that can be obtained in the spectrum. The spectral resolution is the inverse of the total acquisition time. For example, if a phad is acquired for 1 second, the spectral resolution is 1 Hz. The digital resolution of a spectrum is simply the sweep width divided by the number of data points. For a 1D spectrum like proton, we can have a very large number of data points like 16384 points. Whereas when we are recording in 2D, a 2D spectrum, then the same proton signal will be recorded for 2048 or so data points. If n points are sampled in the time domain, then a total of n points will be used to represent the spectrum in the frequency domain. Scan repetition rate. Multiple scans are acquired and added together in memory to increase the signal to noise ratio of the spectrum. While the summed signal after n scans is proportional to n, the total noise level scales as square root of n, so that the signal to noise ratio is proportional to square root of n. Therefore, 4 times as many scans are required to double the signal to noise ratio. The acquisition of multiple scans also allows the phase cycling of the pulse and receiver phases. It is important to repeat each scan at a slow enough rate such that the magnetization returns to or near to thermal equilibrium before the next scan is started. If the pulse rate is too fast, spin lattice relaxation cannot restore the population difference between the ground and excited states. Consequently, the net magnetization along the z-axis prior to each scan drops with each successive scan, and the population of the ground and excited states may become equal. This is referred to as saturation of the transition. Saturation can be avoided by waiting 4 to 5 times T1 between scans to allow sufficient time for spin lattice relaxation to restore thermal equilibrium. In modern experiments, this is also achieved by gradient purge pulses. Dummy or steady state scans. Since it is generally not possible to have the magnetization return to its equilibrium value at the beginning of each scan, it is often useful to collect a number of dummy scans prior to the actual data accumulation. These scans will place the magnetization at the steady state level that will be present during the experiment, reducing potential artifacts from changes in the signal intensity during the first few scans. If decoupling is used in the experiment, which causes sample heating, then the dummy scans will also bring the sample to thermal equilibrium. Typically, 8 dummy scans are sufficient to bring the magnetization to its steady state values, while more dummy scans are required for temperature equilibration if decoupling has been applied during the experiment. Phase cycling and artifact suppression. This is a very important aspect of modern pulse programming for various experiments. The process of acquiring data with different pulse and receiver phases is called phase cycling. The phase of the excitation pulse and the phase of the receiver are changed in a defined way over a number of scans. Summation of the data from all of the scans in the cycle will result in the suppression of spectral artifacts. The phase cycle suppresses instrumentation errors associated with quadrature detection. Much more involved phase cycles are used to suppress unwanted signals in multidimensional NMR experiments, where this is a usual fare. Shifting the pulse and receiver phases by pi will remove DC offsets from the overall FID, and a phase shift of pi by 2 will remove the effects of quadrature imbalance. These two phase shifts can be combined into a complete phase cycle involving the following 4 steps of the receiver phase and pulse phases. 0 is equal to x, pi by 2 is equal to y, pi is equal to minus x and 3 pi by 2 is equal to minus y. This phase cycling is called as cyclops. It helps in simultaneous suppression of DC offsets and quadrature imbalance. So this brings us to the end of this module, and let us summarize. Detection of NMR signals involves the receiver coil, preamplifier, mixer, filter, digitizer and the memory of the computer. Quadrature detection allows the determination of both the sign, positive or negative, and absolute magnitude of the offset frequency. The NMR signal sampling is defined by dwell time, spectral width and Nyquist frequency. The experimental time domain data is converted into frequency domain spectrum by using the fast Fourier transform FFT algorithm, which generates Lorentzian Lineshapes. The raw NMR signal is zero-filled, convoluted with a window function, Fourier transformed, and the frequency domain signal is phased, referenced and baseline corrected. For a good spectrum, the pulse width is to be properly set, the transmitter offset and spectral width have to be carefully chosen, and the receiver gain should be optimally set. The acquisition time and the scan repetition delay have to be chosen carefully with a few steady state scans. Scans are repeated as multiples of the scans needed for phase cycling and are averaged. Thank you.